Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory linear algebra based on my book, Retrolinear. The subject of this lecture is elementary matrices and their inverses. So let me remind you of what elementary row operations are. There are three operations on a matrix that we are called elementary row operations. The matrix walks through the door. There's three types of things you can do to it and call them elementary row operations. One is that you can multiply a row by a non-zero constant. You cannot multiply by zero because that would wipe out the whole row, and there's no going back if you do that. But you can multiply a row by a non-zero constant. You can also switch two rows, and the third one is that you can replace one row with the sum of that row with a multiple of another row. So multiply some row by a number and then add it to another row. The only row that gets changed is that row that gets added to. These are the three elementary row operations, and we use them quite often. In particular, we use them when we want to solve systems of equations. They also have plenty of theoretical and other purposes, as we shall see. I also want to remind you of what row equivalence means. If you have two m by n matrices, they might look very different, but if you can start from one, do elementary row operations and get to the other one, they're called row equivalent. So if you can get B from A by a series of elementary row operations, then A and B are row equivalent. But I want to see if we can do elementary row operations using matrix multiplication. So as an example, let's look at this matrix M. This is a 3x4 matrix and it's got a bunch of numbers, and we might want to do the following elementary row operation. We might want to add twice the second row to the first row. The question is that instead of doing that, is there a matrix E that will do the job for us? And what do I mean by that? I mean that if you take E and pre-multiply it by M, find E times M. Remember, matrix multiplication is not commutative, so E times M may be very different, maybe than M times E. And in fact, M times E may not even be defined, depending on what size E is. And so, so that E times M is what I want. This matrix that I have here equal to E times M is what you get by adding twice the second row to the first row of M. I've kept the second and third row intact, but the first row has changed and it got added to it twice the second row. Is there such an E? Well, let's look at for a second the sizes. Well, M is 3x4. The resulting matrix is also 3x4. That forces the size of E. First of all, E has to be something times 3 so that you can multiply it by M. But because you want the answer to be 3x4, E will have to be 3x3. So it has to be a 3x3 matrix. And now let's try to think of what this matrix would be. When we multiply E by M, the third and the second and the third row are unchanged. They're not changed. And so to preserve those rows, what we need E to be is like this. So if the second row of E is 0, 1, 0, when you multiply it by M, that second row gets multiplied by the columns of M. And what we want to happen is that we want when you multiply the second row of E by the columns of M, that's when you get the second row of EM. And we want the second row of EM to be the same as M. So we want when you multiply E by the second row of E and find the dot product by the columns of N, we want to pick out the elements in the second row. And we do that by having E be 0, 1, 0, so that when you make it a column vector and multiply by those columns, those zeros eliminate whatever it is in the first and the last row of M, and that one picks out the second row. And similarly, to pick out the third row and leave it intact, we want the last row of E to be 0, 0, 1. Now, what about the first row? The first row times M is what gives us that first row of EM, and that's something that we do want to change. And what we want is that every time we multiply, we want to get twice the second row plus the first row. And for that, what we need is that the first row of E to be 1, 2, 0. Because again, that 1 picks up the first row, that 2 multiplies the second row by 2, and then they get added up. So if you have E equals 1, 2, 0 as its first row, 0, 1, 0 as second row, 0, 0, 1 as its third row, then EM will be what we want. And in fact, this E doesn't work just for M, it works for any 3 by K matrix. That E times any 3K by matrix results in one elementary row operation, one very specific one, twice the second row is added to the first row. So this E, this matrix E, its job, its reason for existence, this is what it does in this world, this is what has been brought to this world to do, is to do that elementary row operation. You put it in front of a matrix and multiply it by that matrix, as long as it's the right size, it will do that elementary row operation for you. So now let's think about this a little bit. So this was the matrix that we had. E is 1, 2, 0, 0, 1, 0, 0, 0, 1. And let's ask, where did it come from? Like, how could we have guessed that this matrix is doing that one elementary row operation for us? And if you notice, it's actually not that far from the identity matrix. What do I have to do to the identity matrix to get this this matrix E? And the answer is, you've got to do exactly the same elementary row operation. What elementary row operation? Multiply the second row by 2 and add it to the first row, but do that to identity, the 3 by 3 identity, and you get E. So if you want the matrix that adds twice the second row to the first row, you do that operation to identity, you get a matrix, and that matrix does the job for you. If you take that matrix and multiply it by any other matrix, then twice the second row is added to the first row. So here's what happens. You start with identity, you add twice the second row to the first row and substitute that for the first row, and you get our matrix E. So again, the same elementary row operation that you apply to identity to get E, when you multiply E by other matrices, it does the same elementary row operation for you. So here's another example. If you start with identity and switch rows 2 and 3, you get this matrix F. And this matrix F then, if you multiply it by other matrices, its job in the world is to switch the rows 2 and 3 of any 4 by K matrix. If M is any 4 by K matrix, then Fm is M with rows 2 and 3 switched. So this matrix F does that. And there's plenty of these matrices around, matrices that you've gotten from identity matrix by doing one elementary row operation, and their reason for being in this world is to do elementary row operations for you. So now we can give them a name. These are called elementary matrices. So E is an M by N. They're square matrices. They have the same number of rows as columns. So if you have an M by N matrix, then it's an elementary matrix if it can be obtained from the identity matrix by a single elementary row operation. Okay, now here's a theorem. If E is an elementary matrix, then that means that E is obtained from performing a certain row operation on identity. Then if A is any other M by N matrix, then the product EA is the matrix that's obtained when the same row operation is performed on A. So this theorem says what I was implying in the previous slides, meaning that if you start from with an elementary matrix that you got from identity, because by definition you've got it from identity by a single elementary row operation, and if you take that elementary matrix and multiply it by a matrix A, then the result is that you've done an elementary row operation on A. Now, I'm not going to go through a proof of this. The proof of the pudding is in the eating. This is basically, you have to do 3 cases and say, okay, if this is this kind of an elementary matrix, let's just multiply it and see what it does. If it's this other kind of an elementary matrix, let's multiply and see what it does also. So, and then that's sort of a tedious proof that doesn't really give us that much insight other than the fact that it works. And best is done by looking at a bunch of examples, and then you're convinced that it works. Now, a corollary of this is that if you have 2 M by N matrices, and if they happen to be row equivalent. Now, remember what that meant? Row equivalent means that you can start from A, do elementary operations, but not necessarily a single one, and get to B. We can reword that now in terms of elementary matrices. So to go from A to B, you might do 47 elementary row operations, but every one of those is multiplying by an elementary matrix. So being row equivalent is the same as saying you start with A and you do one elementary row operation, that's E1, that gets multiplied by A.
Then you do another one, that's E2. Then you do another one, that's E3. Every time you multiply the new E by the result of what you had before, because those are what you got after you've done so many elementary row operations, and you're doing more and more elementary row operations. And supposedly you will eventually get B. So this is if and only if means that if A and B are row equivalent, then you can write it like this. Then you can say that, okay, I start with A, do elementary row operations, and get to B. And instead of doing each one of those elementary row operations, you can multiply by elementary matrix. On the other hand, if B is EK times EK minus 1 times EK minus 2 all the way times E2 times E1 times A, and these E's are all elementary matrices, then that means that there it is, the recipe for how to go from A to B using elementary row operations. Each one of those is a single elementary row operation, and therefore A and B are row equivalent. So this is just a translation of what a row equivalent means in terms of matrix multiplication. Now, one of the reasons we're interested in, so one reason we're interested in elementary matrices is because of their connection with elementary row operations. And elementary row operations, as we have seen in solving systems of equations, are quite crucial in linear algebra. Almost everything we do in linear algebra eventually ends up being something about the system of linear equations, and systems of linear equations, we solve them by doing elementary row operations. But a lot more is true than that in terms of why elementary row operations and elementary matrices are useful for us. One reason why that is that one of our quests is to find out about invertible matrices. Which matrices are invertible? Invertible means a matrix A is invertible if there's some other matrix, a friend, matrix B, such that AB and BA are both identity matrix. First of all, they have to be square matrices for that to be true. And elementary matrices start us on a path regarding these guys. So every elementary matrix is invertible. That's one fact about them. So elementary matrices give us a whole collection of, a very rich collection of invertible matrices. If your day job is finding invertible matrices and your boss comes in every day and asks you, give me a new elementary matrix, well, this gives you as much as you want. Maybe they're not that complicated, but they are all invertible if this theorem is to be believed. And in fact, the inverse of every elementary matrix is also elementary. So not only a matrix that's invertible, that means it has an inverse, and we're saying that every elementary matrix is invertible, and the inverse is also an elementary matrix. Now this combined with something we know about invertible matrices, i.e. that if you have two invertible matrices A and B and multiply them, the result is also invertible. Why? Because the inverse of AB is B inverse A inverse. If you take AB times B inverse A inverse, you get identity. And if you take B inverse A inverse times AB, you get identity, because matrix multiplication, although not commutative, is associative. So you can put parentheses everywhere you want. But that was something that we had talked about before. So product of invertible matrices is invertible. And if elementary matrices are invertible, then the products of elementary matrices are invertible. So that's that. Now this is a very rich collection of invertible matrices. Okay, so now let's prove that theorem. So what's the proof that elementary matrices are invertible and the inverse is elementary also? So the proof goes as this. There's one big insight, and the insight is that every elementary row operation can be undone. In fact, that's why we had elementary row operations, because when you started with a system of equations and did an elementary row operation, then if you didn't like it, you could go back. And that's what assured us that a system of linear equations has the same solutions exactly as another system of linear equations that you got from the first one by doing elementary row operations, because those are all, those operations all you can go back and forth. And so if you, from this, you can conclude that, and then from that, you can conclude something else, and eventually you conclude x is 5, you can come back and get that x equals 5 is a solution to the first one. And the point is that not only you can undo it, but when you undo it, you also use an elementary row operation. Let's see what I mean by that. So consider some matrix M, and say that you want to do elementary row operations on M. So one elementary row operation you could do is switch to rows I and J. Well, you can undo that by switching rows I and j again. And that switching row I and j again is also an elementary row operation. So here's an elementary row operation, or actually a type of elementary row operation, and you can undo it by another elementary row operation. Another elementary row operation is multiplying a row by a non-zero constant. Well, if you didn't like that, you can multiply that row by 1 over that same constant, and you have undone it. And because alpha is non-zero, 1 over alpha is always defined, and you can always do this. This is one of the reasons, I mean, the main reason why you never multiply. Multiplying a row by 0 is not an elementary row operation. The last one is that you add alpha times the ith row to row j. Now here, by the way, alpha can be 0. If you multiply 0 times the row I to row j, well, you haven't done anything. Row j stays put. I mean, you've wasted your time, but it's allowed. I mean, wasting time is allowed. So you can add a multiple alpha to row j, of row I to row j. And if you don't like that, well, multiply row I by minus alpha and add it to row j, and that operation is done. Okay, so how is that related to elementary matrices being invertible? Well, let E be an elementary matrix, the one that I want to see whether or not it's invertible or not. Now, E is one of the, E is associated with one elementary row operation, and that elementary row operation, whatever it is, can be undone. And so let E0 be elementary matrix for the operation that undoes E. So for example, if E is the one you got by switching rows 2 and 3, E naught is also the same one, the one that you get by switching rows in 2 and 3. If E is the one you get by multiplying row 47 by 81, then E naught is the one that you get by multiplying row 47 by 1 over 81, and so forth. Now, then we asked, what's E0 times E? Well, the answer to that is identity. Why? Well, because E, how did we get E? We did some elementary row operation to identity to get E. And then E naught, when you multiply E naught by E, it undoes that. It does the undoing operation. So undoes that to E, and when you undo that operation on E, E already had done the same thing to identity to get there. If you undo that, you get to identity back. And the same is true for E times E0, because E0, you did something to identity to get E0, and then E undoes that. All of those undoings are both ways. The thing on the left undoes the thing on the right, and the thing on the right undoes the thing on the left. And because of that, because E0 is identity and E0 is identity, we get that E0 is E inverse, and E0 is an elementary matrix. So elementary matrices are invertible, and their inverses is elementary as well. Now, again, if you look at a whole set of elementary matrices multiplied together, what does that mean? That means that you started with identity and did one elementary row operation to get that first one. And then you're applying other elementary row operations, and that's the product of elementary matrices. And we just proved that such a thing is invertible. So if you start with identity and do elementary row operations, as many as you want, you will always get invertible matrices. In the next lecture, we will be talking about whether or not there are other types of invertible matrices, and spoiler alert, they're not. Those are the only types of invertible matrices that are all invertible matrices are a product of elementary matrices, but that's a part of a nicer, bigger story. So for example, the inverse of the matrix 1, 2, 0, 0, 1, 0, 0, 0, 1 is 1 minus 2. Why? Because well, the first one is an elementary matrix that you got by adding twice the second row to the first row. You didn't like that. You have to add minus the second row to the first row of identity to get its inverse. So again, this is an elementary matrix and its inverse, and they correspond to operations that undoes the other one. Or this one here, for example, 3, 0, 0, 1 is the elementary row operation of multiplying the first row by 3. And if you want to undo that, you multiply it by 1/3. And so if you take these matrices and multiply them either way, either the first two or the second two, you will get the identity matrix. So that's the end of this lecture. I've tried to make these lectures as short as possible.